All right, go ahead and take your homework out. Books open to page 156. You did questions 8 through 12 and problem 3. 8 through 12, problem 3. Good, let's take a look at these questions. First of all, we're going to get to the problem in a moment. Question number 8 asks this: how can a spring constant be determined? What did you put for your answer, Kendall?
A spring constant can be determined by multiplying it by the amount of stretch and divide it by the force.
Audrey?
A spring constant can be determined using Hooke's law.
Okay, you could just say using Hooke's law. Kendall was kind of right, though. I kind of like that Kendall started to explain it. She was just a little off.
A spring constant can be determined by adding a mass until it reaches equilibrium.
Okay, so basically you divide the force that is used to stretch it, divide the force by the amount of stretch. That's all. Let's see, number 9. What forces are in balance when a mass hanging from a vertical spring is at equilibrium? Let's go back to Michael.
The forces in balance when the springs equilibrium are weight and tension force.
We could call it tension, I suppose, though it's not quite a tension. We had another name for it earlier in the year, Audrey. So the weight has to balance with the... Kendall? Restorative force. Weight and restorative force have to be in balance. Number 10, define period, amplitude, and frequency. Let's start with Audrey. Define period.
It's the full time of one oscillation.
Good. How about what's the next one? Amplitude, Michael.
Is the maximum displacement.
Okay, from equilibrium. And then frequency, Kendall.
Is the number of oscillators that occur per unit time.
Good, oscillations per unit time. Let's see, number 11. What is simple harmonic motion, Audrey?
Periodic motion that follows the same path over the same time interval and is caused by a restorative force that is proportional to displacement.
Very thorough answer. Could have written it better myself. And then number 12. Distinguish among periodic, oscillatory, and simple harmonic motion. All right, Michael, what'd you have?
Periodic motion is one-fold movement during the unit time. Oscillation is back and forth motion, and harmonic motion is a combination of oscillation and repeated periods.
No, I mean, I don't know that the book comes out and clearly says it, so you really had to kind of read for understanding to get this. I don't know that that's a bad effort. Curious to see what Kendall had.
Periodic motion is the back and forth motion over the same amount of time, repeated in the same laps. Oscillatory motion is if it repeats back and forth over the same path in the same length of time, and simple harmonic is periodic motion that follows the same path over the same time interval.
You were doing so good until the very end, because basically your way you defined oscillatory and simple harmonic was the same. Audrey?
The only thing different that I had was simple harmonic motion is caused by a restorative force proportional.
There we go. It's kind of like, take you back to geometry class, and I'm getting a little ahead of myself, but where we talked about quadrilateral, it's just a really broad term. Well, more specifically would be a parallelogram, opposite sides are parallel. More specific to that could be like a rectangle, because you have a right angle. And even more specific could be a square, because a square is a rectangle, which is a parallelogram, which is a quadrilateral, kind of that stacking doll effect type of thing. And that's kind of what's going on here. Periodic is kind of a broad term. Oscillatory is more specific, and then simple harmonic gets more specific still. We'll get to all of that a little bit later on. All right, not bad at all, though, on the homework. Pleased with the effort there. We'll take a look at problem 3 here in just a moment. Let's review, though. We were talking about uniform circular motion. And what is uniform circular motion, Kendall? Motion that is circular and uniform. Very good, excellent. All right, next question. Okay, can expound on it just a little, but it's really close to the right answer, actually. Audrey, help her. Uniform circular motion. What is circular, class?
Circle.
The path of the motion, right? So the path is circular. What is uniform?
The same distance from
the same speed. So a constant speed in a circular path. Okay, so what is uniform circular motion, Kendall?
The same No, the same speed in the circular path.
Good, circular path and constant speed, right? The same speed constantly throughout, or a constant or uniform speed. Now, for an object that's in uniform circular motion, it goes around and around and around in the same circular path at a constant speed. Okay? That constant speed, circular path, well, it may be at a constant speed, but class, it is not traveling at a constant velocity. Why is the velocity not constant, Michael?
It constantly changes direction.
It constantly changes direction. One moment my hand's going up, now it's slightly going forward, now it's only forward, now it's starting to come downward, now it's straight downward, now it's coming back toward me, now it's really coming back toward me, now it's going back up. Like, direction's constantly changing. And so if direction is changing, velocity is changing, and in general, any change in velocity, class, is called acceleration. But here the acceleration doesn't involve a speeding up or slowing down, which means the acceleration has to be perpendicular to speed. In which direction is the acceleration if the object is going around in a uniform at the same speed? In which direction is the acceleration? Kendall? For an object in uniform circular motion, acceleration is always, anyone?
Out.
Ooh, in. Toward the center. All right, so class, where is the acceleration for an object in uniform circular motion? Toward the center of the circle. Now, what do we call this toward the center acceleration, class? Centripetal acceleration. So this inward acceleration toward the center is centripetal acceleration. The object's speed goes that way, the acceleration goes perpendicular, so it has no effect whatsoever on the speed. That's the only way. If there were any component of acceleration that were in the same direction, then you would have a speeding up effect. So the only way it could have no effect on speed is if it's exactly perpendicular, which means it has to go toward the center. But acceleration doesn't happen, Newton said, unless there is an outside force present. What do we call a force that causes centripetal acceleration? Centripetal force. There is some centripetal force pulling inward. Now, for every action, there's an equal and opposite reaction force. So what is the reaction force tugging away against the centripetal force? Anyone?
No.
It's often confused for inertia. Centrifugal force. The centrifugal force. So it's the reaction force. Do you remember what centrifugal meant?
Center seeking.
That's centripetal. Centripetal is center seeking. Centrifugal is center fleeing, right? And so there's this center fleeing force that's the reaction force. But the centripetal force is more what we're concerned about. And I gave you 3 examples of common centripetal forces. Forces that cause an object to be tugged inward and therefore stay in a circular path. Do you remember one of those centripetal forces, Kendall? For instance, a yo-yo, swinging around your finger. What is the force that causes the yo-yo to keep going in a circle? Tension force. Can you give me another example besides tension of a centripetal force, Michael?
Friction.
Friction. Remember the race car yesterday? We said that you need friction to help the car make that turn. Icy road? Bye. Right? A bad day. Can you give me another example? Or for that matter, anyone done go-karts before? Ever done go-karts on a slick track? Okay, very different ballgame, right? Yeah, anyway. Kind of the same idea, right? Less friction, it's harder to make those turns. You have to actually exercise a little bit of skill in maneuvering versus the other course where there's plenty of friction. You just literally jam the gas down the entire time and never let up. I mean, there's no real skill other than navigating the turn really tightly and cutting people off and spinning them out of turn. Anyway, but I digress. So we said friction is a common example of a centripetal force. Tension. There was another one. Gravity, right? Gravity is what keeps the planets moving in their orbits and the moon going in its orbit and things like that. We can think of a couple more. For instance, if an airplane were to bank and go in a circle, what would be the centripetal force there? Air resistance, which you could argue is a type of friction based on the way we define friction, but air resistance certainly. We also looked at one when a roadway is banked. There are 2 centripetal forces that allow the car to make the turn. Obviously friction, pushing back against the car, pushing it back inward. But what was the other one?
Gravity.
Let's get a little more specific.
Gravity in X.
The weight specifically in the x, right? That pull inward, downward, down the slope. So weight in the x could also be a centripetal force. Now, to find centripetal acceleration, what is our equation, Kendall?
V squared over R.
V squared over r, and then centripetal force, Michael,
MV squared over R.
mv squared over r. So we have these two equations so far in this chapter, and we use those to help us solve problem number 3. And let's see, what do we have? Go ahead and read number 3 for us, if you would, Audrey.
What centripetal force is needed to keep a 2.5 kilogram model plane orbiting in a 45 meter radius if it completes one orbit in 12 seconds?
Well, speaking of air resistance, all right. So we have the mass of the plane given to us, class.
2.5 kilograms.
2.5 kugas. It gives us the radius of this circular path of the airplane, class.
45.
45 meters. We worked a couple problems yesterday. We were given a diameter, remember. We had to cut it in half. They already gave us the radius. That was nice of them. Then it says 12 seconds. What is 12 seconds, class?
The time.
That's time. And it says, what centripetal force is needed? Well, for force, class, I need what 3 things?
Velocity squared.
Velocity squared, mass,
and
radius. So as far as finding the centripetal force, I know the mass, I know the radius. But they didn't give me the velocity. Instead, they gave me a time of 12 seconds. But it's important to note, the 12 seconds, class, is the time needed for one orbit. If it's a circular orbit, class, we could say that this one orbit is the distance around. Not perimeter, that's a polygon. Circumference, right. So the distance traveled is the circumference of a circle. We had an example problem like this yesterday, you might recall. How do I find circumference of a circle? Pi r squared is area of a circle. Pi d or 2 pi r, which the 2r is the diameter, right? So this distance that the plane is going to travel, an orbit, in other words, is 2 pi r. So we'll take 2 times pi times the radius, which is 45 meters. And if we multiply 45 times 2 times pi, how far is the plane traveling?
282.7.
282.7 blah, blah, blah meters. And it travels that distance in 12 seconds. How do I find velocity? d over t. So if I know the distance is 282.7 and I divide that by 12 seconds, what is the velocity of this plane?
3.56.
That's a really good model airplane. That's about 45 to 50 miles an hour. That thing's humming. All right, that's pretty cool. All right, so the velocity that we needed, and that was what made this problem a challenge, was having to find that velocity on your own. Thinking through some of the things we'd seen in example problems, thinking through something we'd seen in a previous chapter, and getting that velocity. Did anyone figure out that velocity? Does it make sense now? All right, go ahead and finish the problem out now. And how much air resistance we'll need to push on the wings of the plane. Now, obviously, there's wind pushing on both sides of the wings, right? So we need more push on the underside of the wing than we have on the top of the wing, so that way it pushes it back inward. What do we get for that force, class?
31.
Or round it off to 2 sig figs? 31.
Meters per second.
Well, it's force. Newtons. 31 newtons of centripetal force needed. All right, questions on this now that we've seen it done? Questions now that we've seen it worked? All right. Let's go and move on then to what you did talked about in your reading last night, or read about, I should say, in your reading last night. You want to get this term in your notes? Periodic motion. Periodic motion. Periodic motion. When we talk about the word period, Period always has this idea of time, right? In history, you talk about different time periods, right? Or sometimes call them ages, right? Like the Elizabethan age, the Victorian age. We just ended the second Elizabethan age in England. Queen Elizabeth just recently passed. There were perhaps some snarky comments made in a study hall, I heard. Anyway, but an age, or you could call it an era, or you could call it a period, right? Different time periods in history. Well, period refers to time, so periodic motion refers to motion that is defined in some way by time. Here's your definition. Periodic motion is any motion that is repeated in the same lapse of time. Any motion that repeats itself or is repeated in the same lapse of time. Motion that is repeated in the same lapse of time. Some examples that I might be able to give here. For instance, you ever been to a basketball game and you notice in the basketball game maybe you're watching and the guy dribbles down the court and the ball is down, up, down, up, down, up, down, up, down, up, down, up. Now, of course, the guy can shorten his dribble, right? He comes down lower, down, 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 down. You can almost hear the ball hitting the ground rhythmically. Have you ever noticed that? Or maybe if a guy is about to shoot a free throw, like gets the ball from the referee and bounce, 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 very rhythmically. Well, if that motion is repeating itself after the same lapse of time, that would be an example of periodic motion. I think of if you're sweeping. Now, I used to, the house I lived in had a front porch and garage was on the other side of the house. So there was this long, skinny sidewalk that led all the way around. So the sidewalk's literally only maybe 2.5, 3 feet wide is about it. Very, very narrow, but just so you're not walking on the grass to get back and forth around. So when I had to either blow it off or sweep it off, and we had electric, so I'd have to get the extension cord out, get the leaf blower out, plug it in, blow it off, and then you have to rewind the extension cord. How many have rewound long extension cords before? Just a pain. So I'm like, you know what? There's a broom sitting right here. So I get the broom out, and go back, forth, walk my way down the driveway, or sidewalk rather. Not really thinking, but periodic motion, if it's in the same lapse of time. Back and forth, back and forth, back and forth, back and forth, back and forth. Same lapse of time. So sweeping can be an example there. I think of jumping rope, right? Ever watch somebody jump rope for a while and just constantly over and over and over and over and over and over. Anyway, and or even if it's like the two-step, like the pop, 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 right? Or the one. I mean, you know what I'm talking about? But it's motion that repeats itself after the same lapse of time. That's periodic motion. One of the motions we're going to look at specifically in this chapter is this idea of springs having a repeated motion. By the way, you could even look at swinging on swings, periodic motion, right? Back and forth, if it repeats itself in the same lapse of time. Now, if the child begins to get higher and higher, right, then that's not quite necessarily the same idea, but very close, right? So when we do this, right, we see it going up and down, or down, up, down, up, down, up, down, up, down, up, and so on and so forth, right? You are now under my power. When I snap my fingers, you will say, Mr. Ndasky is the best teacher ever.
Mr. Ndasky is the best teacher ever.
Well, it didn't come from who I was expecting it, but way to go, Michael. All right, you get an extra credit point on your next test. You have not because you say not. Anyway, but we get this idea of this rhythmic motion with springs as well. Now, I do want to point this out. We did this before where we tested springs and we saw how low they would hang and just kind of rest there, correct? At this point right here, this is what we call equilibrium for a spring. If you'll jot that term down. Go and write it as spring equilibrium, because obviously there's different types of equilibrium. And I cannot make a cursive R to save my life. I was trying to help my son with his cursive R's the other day. Yeah, because his cursive R's were coming out like that. And so I'm like thinking to myself, I'm not too great with R's either, but I got to help him get better than that. So I'm like, okay, son, here. Trace that. And I'm like, I should give him a word with it. I don't remember what the word was, but I gave him a word with an R in it. So soon we could practice up, down, and over and stuff. So anyway, yeah, R's are giving him trouble, like father, like son. Anyway, so spring equilibrium is any time that the weight acting downward is equal to the restorative force acting upward. Anytime the weight acting downward is in balance with or is equal to, though opposite in direction, of course, to the restorative force upward. We could say that weight equals negative restorative force. The weight equals negative restorative force. At that point, we have equilibrium. If we were to draw a free body diagram, we have the object, it has weight, and we have restorative force counterbalancing it. No other forces are at play, correct? Now, when that's true, the spring will have stretched a certain amount from its coiled position to a more sprung out position. The amount of stretch we used to represent with the letter X. And we noted that if you hang this mass from this spring, it's stretched that much. Can I get a mental picture? Actually, I've got a second mass that's identical. We'll do that this way. This spring is a little bit thicker. When I hang this same mass from the thicker spring, you notice it does not stretch as far because they have different, do you remember? Spring constants. There was something called the spring constant. And same was true with rubber bands. Remember, we demonstrated rubber bands. And then you got this one, which is very light, and it obviously stretches more. So every individual spring, we said, will have its own different spring constant. And according to Hooke's law, remember, we said that the stretching force, or the tensile force, was equal to kx. Well, in this case, we could say that the tensile force is really weight. And so it equals kx. In which case, we could say that k divided by the x equals the weight over the stretch. Or, since weight is mass times gravity, we could say k equals mg over x. It's not like we haven't done this before, but go and get it in your notes afresh and anew so it's with this section of how we find spring constant. I also want to point out units that you'll see here. Remember, weight would be measured in newtons, and stretch is measured, since it's a distance, going to be measured in meters. So the spring constant may be given to you or may be found in the units newtons per meter. That's one way you might see it. But consider this way. What is mass class? Kilograms. What is G?
Gravity.
Which is 9.80
meters per second.
And we said the stretch is going to be in meters. Thoughts?
Meters.
Where you could just get kilograms per second squared. So you'll get one of two units, either kilograms per second squared or newtons per meter. Now, the one that is frequently used in the book will be newtons per meter because it's really easy to type. Kilograms per second squared is harder to type, and mathematicians are lazy, okay? However, you're going to benefit from thinking, as we move down the road here in a minute, in thinking kilograms per second squared. So that's why I want to show you both of those potential units. Just by way of review, look at page 149. Page 149, let's look at an example problem here. Really, again, we kind of did this in chapter 5 already, but just to kind of refresh our memory a little bit here, we did something very, very similar to this. Read the example problem, if you would, Michael.
A light spring is hanging vertically from a hook when a 450 gram mass is suspended from the spring. The spring has stretched 10 centimeters at equilibrium. What is the spring constant, and how far will the spring stretch if an 8.85 kilogram mass were suspended instead?
All right, so let me go ahead and erase some of the extra stuff here. And so it starts off, we've got a light spring, and then we hang a 450 gram mass. That's about this. Okay, so this is about a pound or so. And and so it's a pretty sizable mass hanging from what they call a light spring. And it only stretches 10 centimeters. I mean, this is I think, my thickest spring. Okay, it stretches way more than 10 centimeters. Well, not way more. About 15 centimeters. So this spring is actually a little bit thicker than my thickest spring. All right? So just, of course, that's also slightly more than 450 grams, so that could have impacted as well. All right, so it wants to know, letter A, what is the spring constant? Class, how do I find spring constant? K equals mg over x. Again?
K equals mg over x.
Well, the m, of course, class here is the 450 grams. Ooh, but you're right, Michael. We need to change that to 0.45. I'll take off the 0, even though, I'm going to look back at the original problem for safe face. 0.45 kilograms. G class, again, we're going to assume to be,
9.8.
and then the stretch it said was 10 centimeters, but 0.1 meters. Obviously, we know meters and meters will cancel. So at your seats, we have the 0.45 times 9.8, divide out the 0.1. And what do we get for the spring constant? 44.1 either kilograms per second squared, which is the units I have left, or newtons per meter. Questions on the first part of the problem? By the way, I don't remember with this fixed spring. I want to say it was around 38 was what we measured it at way back in the earlier chapter 5. All right, but then it says, okay, let's take this same spring and put an 850 kilogram mass instead. So somewhere between these two, okay? So we put a little bit more mass. Well, if we put more mass on the spring class, what should we expect? We should expect it to stretch further, shouldn't we? So we know the spring constant now is the 44.1 kilograms per second squared. We are now putting a mass of point, and then they were nice enough to already put it in kilograms for us. Okay, 0.850 kilograms. And it wants to know the stretch we would get. Of course, with addition to these, we also know our G class is the 9.80 meters per second squared. All right, so if I want to find the stretch, same equation, right? K, mg, and x. But if I want the x by itself class, I'm going to need to alternate. And we'll say that x is equal to mg over k. So take the mg and divide the k. How far would we expect 850 grams or 0.850 kilograms to stretch the spring? Anyone?
0.18 repeating.
Good, 0.18 repeating. Of course, we'll round off to, it is 3 sig figs, right? I did 3 on the last one. Yeah, 3 sig figs. So
18.9.
good, 0.189 meters, or centimeters is easier. So I like what Audrey did just now, 18.9 centimeters of stretch. Any questions on that? Notice we almost doubled the mass. 450 to 850 is almost double. We almost doubled the stretch. 10, that's almost 20, almost doubled, because it's a proportional relationship per Hooke's law. Questions on this? Do you remember doing problems like that? I think we actually did it with the springs. We put a mass on, got the spring constant, put another mass on, checked to see did it stretch like we thought it would. Do you remember doing all that stuff? All right. Next term in your notes, talking about periodic motion class, we said periodic motion is motion that repeats itself after the same lapse of time. But remember I said if you were dribbling a ball down the basketball court, dribble, you kind of hear the ball hit it, bounce, 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 bounce. It's the same motion, right? Down, up, down, up, down. Kind of a little bit of a V shape, right? Because you're bouncing it up in front of you and then going to it, right? And it's not following the exact same path, but it's the same motion in the same amount of time. Well, imagine the player then brings a stationary dribble. Bounce, 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 bounce. And now the ball is literally traveling the same path. Or imagine instead of walking down the sidewalk, sweeping back and forth to get the leaves and grass and stuff off the sidewalk, there's one particular spot, I just stand there sweeping that one spot. Maybe small children got very fine dust and dirt all over that one spot. And it's layered on, so I have to keep sweeping for a while to get all of it off. Yes, my children have discovered the joys of playing with dirt. All right, and we can throw it in the air, make a cloud all over everything. Came out one day, I was like, yeah, it seems like there's some dirt and stuff. And I only sweep, and I'm just shocked how much dirt there is. As I'm sweeping it, there's a cloud forming. I'm like, anyway, but I sweep in one spot for a while. Well, that's what we call oscillatory motion. So periodic motion simply refers to the motion repeats itself after the same lapse of time. Oscillatory motion, OSC, oscillatory motion, does follow the same amount of, follow the same lapse of time, but it follows the same path. So oscillatory motion is periodic motion along the same path. Periodic, same amount of time, but follows the same path throughout. Oscillatory motion, periodic motion along the same path. Now, to come to this, for instance, this is not just periodic motion, this is oscillatory motion. Because it's not just taking the same lapse of time every time, but rather it is following the same path also. Does that make sense? The time is the same, so class it's periodic, but since it's in the same path as well, it is more specifically oscillatory. Always, sometimes, never. Oscillatory motion is periodic. Always. Sure, always, sometimes, never. Periodic motion is oscillatory. Sometimes, only if it's the same path. You kind of get the idea there. Okay, can try to draw some geometry parallels. Stop. Okay. Now, let's talk about what's going on in this oscillation, because we said right here at equilibrium, everything's in balance, right? There is the same amount of weight downward as there is restorative force acting upward, correct? Well, what if I pull down? What have I just done? I've added an additional force downward, haven't I? But the spring didn't snap, which is happy. What if the spring snaps? Then that means I exceeded the ultimate tensile strength, or the, anyway, whatever. So I stretch down further, right? Well, since it's not broken, that means there must be even more restorative force now, correct? Just like, for instance, Kendall's sitting there on her seat, and she has a certain amount of weight bearing down. The ground to support her has to exert a certain amount of normal force. If I lay hands on Kendall, to bless her, of course, then that would increase the amount of force bearing down, so therefore the ground will exert greater normal force, right? We even talked about this, the idea of pushing something versus pulling something. A lot of times a push involves pushing downward and increasing the friction. Well, same kind of thing here. As I bear down, there's now more restorative force. So if I let go, which is greater? Restorative force or weight? Restorative force, right? Weight didn't really increase. I just added an extra force. So if I let go, there's more restorative force upward than weight is downward, correct? So what's going to happen? If there are not a balance of forces, if this force wins, it's going to accelerate, isn't it? Anytime there's a force that wins, you get acceleration. So when I let go, it shoots upward to about here, correct? Now when it shoots upward to about here, you see that the spring kind of condenses inward. It accelerates past equilibrium. Its own inertia carries it forward until it gets about here, and then wait a second. There's almost no restorative force at all. There's just weight. So you know what's going to happen? It's going to go downward, but it accelerates. So it goes past the equilibrium point, back down, until eventually there's an imbalance, right? There's more restorative force up than there is the weight down, and so the restorative force slows its acceleration, right? It shoots down, but then it slows down as restorative force increases until it gets back down here, and now there's so much more restorative force than weight, it can't keep going down. In fact, shoots back up. So it's that imbalance of forces that causes the oscillation. Does that make sense? Now, I want you to consider just a moment a couple of things about this. All right, if I stretch it just a tiny little bit, just the littlest bit of stretch, am I changing the imbalance? Am I creating much of an imbalance? So the restorative force isn't that much greater, is it? So it will accelerate upward, but not a whole lot, right? Whereas if I stretch it downward like this, I've just increased the restorative force a whole lot, haven't I? I thought that might happen. So I just increased the restorative force a great deal, so it shoots upward till it falls off, right? Let me see if I can do it not quite to where it falls off. But you see, now it's moving a lot faster than it was before, right? I mean, you can visibly see it rushing up and rushing down versus here, just little bitty slow movements, right? Greater force, greater acceleration, greater velocity. Make sense? This displacement from equilibrium, whether, okay, so here's the equilibrium position, I pull it down a little bit, or I pull it down a lot bit, okay? That displacement from equilibrium is called amplitude. Go and write that term in your notes. Amplitude is displacement from equilibrium. Now, Audrey and Michael, you will remember this term from pre-calculus, right? As that displacement from the x-axis when graphing sine, cosine, other trigonometric ratios. It's displacement, it's distance away. Well, imagine at the equilibrium position, there's an x-axis. How far down or up above does that oscillation take place? So it's a similar term that may help you guys to remember that it's nothing whatsoever for Kendall. All right, that's the amplitude. Now, In addition to considering the amplitude of oscillation, it's oscillating a big distance or it's oscillating a very small distance, right? That's the amplitude of oscillation. That simply depends on how much extra force was applied. More force applied, greater displacement from equilibrium, greater amplitude of oscillation. Another thing to consider is the time it takes to make one full oscillation. So it starts down, up, down, that's one full oscillation. Up, down, that's a second. Up, down, that's a third. Up, down, that's a fourth, right? Each oscillation takes a certain amount of time. The amount of time it takes to make a complete oscillation is called period, which makes sense considering period means time. So period refers to the time it takes for one oscillation. The time for one oscillation. And there's that silent C in there, oscillation, but it's not osculation. No, it's oscillation, silent C. Do you know what osculation means? Yes, no? I'm getting smiles, so it makes me think you know, but I'm not sure. Okay, osculate means to kiss. Okay, so an it doesn't sound anything like that, right? Like, come here, my darling, allow me to osculate you for a certain period. Like, that would be really nerdy. Yeah, I did that to my wife last night while I was prepping. Anyway, the fate of being married to a physics nerd. And the crazy thing for her is, like, this is new to you guys, but this is the 12th year I've taught this. Yeah, bless her heart, every year it's the same jokes. Anyway, so osculate, right, means to kiss. So oscillatory motion be kissing motion. That's not what we're talking about at Grace Christian School. This is oscillatory, okay, so silent, C, just for the record. Don't you love words that mean nothing like what they sound like? Like osculate. That doesn't sound like kiss at all, does it? Like, kiss is such a happy, pleasant thing, love and all that. Osculate, I don't know. Pulchritudinous is a great word too, you can use sometime, Michael. You know, pulchritudinous means beautiful. It's like, Mom, that is a pulchritudinous dress you're wearing. Or better yet, you get to meet that special someone, you know, in college or what have you. Why, you look pulchritudinous today. You get your face slapped, you know. So anyway, gotta be careful about using words people don't know. Anyway, but I digress. Getting back to, or expectorate. Expectorate, to spit. Right? Expectorate in the wastebasket. Do not expectorate on the floor. I don't know. Anyway. How do we get off on that? Oscillatory motion, yes, period. Time required for one oscillation. Okay. Anyway, period then, since it's time, class is going to be measured in seconds. Period, since it's time, is going to be measured in seconds. Now, there's this idea here, though, obviously, if it oscillates quickly, right? If it takes only a little bit of time for a single oscillation, then in a given amount of time, I will get more oscillations in, correct? For instance, I'm going to do this here. Here, it seems to be oscillating more quickly, right? So in a given length of time, I will get more it's kind of swinging too. I'll get more oscillations in a certain amount of time. This number of oscillations per unit time is called frequency. Frequency. It's the number of oscillations per unit time. Usually thought of as the number of oscillations per second. I don't know, maybe I'm just weird, or maybe my kids are weird. Chloe's just an affectionate, sweet little girl. And so she comes, gives Daddy a hug. So I'm just going, all over. Okay, more oscillations per unit time. Anyway, number of oscillations per unit time is called frequency. It's measured in oscillations per second, but we don't actually quantify the oscillation as a unit. So it's just per second, which, again, Audrey and Michael, you'll remember that unit for angular velocity. All right, so you're already familiar with this per second. The other unit you'll see instead of per second, because it's kind of awkward, is hertz. H-E-R-T-Z. Cycles per second or oscillations per second. So frequency measured in oscillations per second, or hertz. Now frequency then, you understand, the longer it takes for one oscillation, the longer it takes for one oscillation, the fewer oscillations per second, correct? So then, for instance, if it takes 5 seconds for a single oscillation, then a fifth of an oscillation will be accomplished in each second. But if you do a fourth of a second for a single oscillation, which it's not going nearly that fast, but if you got an oscillation in a fourth of a second, you can do 4 oscillations per second. It's simply going to be the reciprocal. So frequency is simply the reciprocal of period. We'll represent period with the letter T for time. Capital T, by the way, not lowercase t, which is a generic time, but capital T specifically referring to a period of some kind of repeated movement. So F equals 1 over T. It's the reciprocal of the period. Now, let's consider then the period. Because you notice when I have this same mass, in fact, we've got both of these and they're the same amount of mass, right? So I put these two masses here, I pull them down. One of them is moving much more quickly than the other. Which one appears to be, it's not jiving at all, is it, right? That bothers you? Which one is clearly moving quicker, class? The one on your right or the one on your left? The one on the left is swinging now and clearly moving more quickly, right? Well, it's got a thicker spring. Think about it. The thicker the spring, the stronger it is, correct? It should be able to apply more force. More force means more acceleration, means more rapid movement, means it's going to take less time. So the spring constant, if the spring constant is big, the time is small. However, okay, it's taken a very considerably long time, even greater contrast if we put these two next to each other, right? I mean, this one just bump, and the other one's whoa, whoa, whoa. You ever feel like your brain's doing this sometimes? Anyway, all right, so, not in this class. So clearly the spring constant, if it's a lower spring constant, a weaker spring, it's going to take a lot more time. So spring constant is inversely proportional to period. What about amplitude though? Right? Let's go with the medium spring because I think that'll be the easier one to record. We may do it on both. Let's take this medium spring here, and I'm going to pull it down just a little bit here. Ready? And you clap with me every time it hits the bottom. Okay? So we're going to start at the bottom and clap with me when it hits the bottom. Okay, kind of got a feel for the rhythm, right? All right, now I'm going to pull it down just a little bit and let's clap the rhythm. What do you notice about the comparison of the rhythm?
The same.
Felt the same to you? Let's try it on a different spring. All right, Audrey, did you feel like it felt about the same? Okay, so let's put it on this spring, okay, and we're going to pull it on just a little bit, okay? Okay, now let's pull it down a lot. You're almost impatient waiting for it to get to the bottom, aren't you? What did you notice about it this time?
A bit longer.
Yeah.
Okay, now let's put it on this spring here, which I fear. Okay, now let me pull it down a lot more and see what happens. It falls off. Of course it does. All right. I think we need a little more mass on the thick spring. It's life on the front row, Kendall. All right. It's always the little one. Get rid of the little one, he said. I didn't realize he'd do it this way. Okay, let's try a thicker one, okay? So, okay, and now let me pull it down just a little. Okay, so. Thoughts? Still feels the same, but it actually was pretty much the same on the other spring as well. I do have a timer. We don't have time to set it up today, but we will do a lab where we'll actually set up a timer that'll record as it goes through. Amplitude doesn't do anything. Amplitude doesn't affect, period. Now, why would this work? Because intuitively we would think, well, if you pull it down further, surely it should take longer, right? Why doesn't it? Because although it has a greater distance to travel, there's a greater imbalance of forces, right? Greater imbalance of forces, greater acceleration, greater velocity. It moves faster, but it still takes the same amount of time to oscillate. So amplitude doesn't mess with it. We said the spring constant does though, right? Lighter spring, greater amount of time. Let's consider, let's go back here for a moment. Let's kind of clap the rhythm for 200 grams, all right? So I can pull it down however much I want because it really doesn't matter anyway. All right, now let me put a little bit more mass on and let's see what happens. Besides, it stretches a lot more. Thoughts? Way slower, okay? Let's go back to the 200 here, just for comparison's sake. Okay, let me go 100. Oh no. Obviously it's faster, right? And so we see that as you decrease the mass, you're also decreasing the time, right? It's quicker, less time if you have less mass. When we put the greater mass on, it took a lot longer. I mean, I don't know if we can handle this much. Oh, let's not do it on that one. So okay, you see it taking just forever to get through. So mass is directly proportional to time. Now, it's not, though, proportional in the same sense that we would think of. There's actually, interestingly, a bit of a square root relationship. It's not direct where if you doubled the mass, it doubled the time. Or if you cut the mass in half, it made the time a half, right? It's not quite that relationship. Instead, to find period, t is going to be equal to the square root of m over k times a set constant value. And interestingly, uniform circular motion comes back here because it is cyclical. It's like the same amount of time, and the constant relationship between that square root and period is 2 pi, one cycle or one revolution for those in pre-calculus. So this is the next equation for you to know. We'll practice with it tomorrow. T equals 2 pi times the square root of m over k. All right, you have no homework this evening. We'll pick up more with that in our next lesson. You have a wonderful rest of your day, and you are dismissed.